Hello everybody, welcome back to the second video of the function series. This time I have a very interesting topic to discuss. It's gonna be the sine function. So if you're curious as to what this picture I've drawn is, let's call it the Ferris wheel or something like that. So basically what I want you to imagine is there's a kid sitting on like a sort of trolley, and this trolley starts out from this point and makes its way across the circle. So it starts over here and reaches the topmost point and then goes back down and then goes beneath the surface and then back to the original point. Let us say that this spins around super fast. I mean, the trolley moves really fast. So in about 1.5 seconds, it reaches the topmost part, and in about 3.1 seconds, it goes back to zero height, and at 4.7 seconds, it reaches the bottommost part, and at exactly 6.2 seconds, it reaches, not exactly, but around 6.2 seconds, it goes back to the original part. Well, these are not random numbers. 1.57 is approximately pi by 2, and this is approximately pi, and this is approximately 3 pi by 2, and this is 6 pi, but I've not written it over here. You can just imagine it yourself. So what's the point of having such a picture in mind? Well, in order to understand the sine function, you have to understand what the need for sine function is. So let's say that the kid placed over here is wearing like a sort of smartwatch which can keep track of how happy the kid is. Let's say that the kid likes tall, or like the kid basically likes height and he hates depth. So it is kind of intuitive that the kid is initially neutral in happiness over here, and as the trolley climbs, as it's climbing, his happiness increases gradually, and over here his happiness is max at 1.57 seconds. And then there is a gradual descent of his happiness. He still is happy, but his happiness is decreasing from 1.57 seconds to 3.14 seconds. And at 3.14 seconds, he's back to being neutral. And after this, he starts descending downwards. And now he starts becoming just a little bit unhappy. And he's the most unhappy at 4.71 seconds. And at 6.2 seconds, which is 2 pi time, he becomes neutral again. But the thing is, let's say that the tracker is constantly sending me the happiness status every, let's say, 0.1 seconds. So I get like a graph. So initially over here, the person's happiness is at 0. So let this be time. So this is time, and this is happiness. So I'll just write the emoji. So initially at time is equal to 0. He's over here. Basically his height is 0, so he's neutral. So he's at 0 happiness. And let's say it sends me a report over here. So over here his height is something decent. So he's a little bit happy. So after some time, he is a little bit happy, and on the happiness scale, he's over here. And let's just make this as unhappy. And after some time, I get another notification over here, and as you can see, his happiness has increased. And there's a point of time at pi by 2 seconds that he is maximum happy. And it gives me this kind of notification. And let's say the next notification I get is over here. And as you can see, the height over here is less than that of the height over here. So even his happiness corresponds to the same, and it will be somewhere around here. And over here, he's going to be a little bit lesser in happiness, and at 3.1 seconds, he's back to being neutral. And after 3.14 seconds, his height gradually decreases and his unhappiness increases. So initially it's a little bit less, and as we cover another pi by 2 angle, the unhappiness increases to a maximum at 4.17 seconds. So it's gonna be a similar graph. So that is, and at 6.2 seconds, it's gonna go back. And let us say, instead of getting a notification every 0.1 seconds or something, I get it every millisecond. And that time, I'm basically gonna get more dots over here. I hope you can understand why. And let's say instead of getting notifications every millisecond, I start getting it every microsecond. The dots are gonna become finer and finer and finer. And if I make it such that the cooldown for notification tends to 0, the line becomes super smooth. And what you essentially get is a sine graph. And you might get the question, how does it matter? Like, I'm talking about height, but in school you've always learned sine is equal to opposite by hypotenuse. So you might wonder, how come you have told us now that sine is basically the height of the trolley, while actually it's the ratio of the height and hypotenuse. And I'll just tell you this. Consider that the Ferris wheel is of radius 1 meter. So that time what happens is you just get opposite divided by 1. This is opposite, not 0, okay? So what you get is opposite by 0, which is basically opposite. And in a triangle, this is the opposite side and this is the hypotenuse. And over here, the opposite side is basically the height that I've been talking about all along. So essentially, the sine graph is basically the height of a moving point or a moving trolley on a Ferris wheel, and it tracks the height as a distance as a function of time. And since maths can be interchangeable with variables, essentially what if I replace happiness and time with x and y? So let us go back into learning about the trigonometry graphs. So I'm pretty sure you guys understood sine and cosine, but I will explain it once again. So you have your sine like this and your cosine somewhere like this. And the most important part of sine and cosine is superposition of them, meaning how you would tackle a problem that had sin x plus cos x. Well, let us try graphing it ourselves first to build up some sort of intuition. So let us consider this as 0.1, this as 0.2, this is 0.3, 0.4, 0.5. So let us mark the same 5 points over here, 4 and 5. So let us just, so if this is sin x and cos x, let us graph sine plus cos. Okay, so at 0, if you add these both graphs, take a point on sin x, which is this point, and take a point on cos x, which is this point. So 1, I mean, you should know this, but this is 0 and this is minus 1. So 0 plus 1 gives me 1. So if I wanted to sketch the graph of sin x plus cos x, I would start off at 1 over here. So at time is, at x equals 0, you have 1. And at this point, you have 0 plus 1 again, which again gives you 1. And over here, you have 0 plus negative 1. So you have a negative 1 over here. And over here, you have 0 plus negative 1 again, which gives me a negative 1. And when I go back to the last and final fifth point, I get 1. So now, the question is, how am I supposed to connect these to get a smooth curve? Because understand this, sin x is a smooth curve, cos x is a smooth curve. So adding them is going to give me a smooth curve again. And to get the resulting graph, let's take a point in between. So this is something like, this is 1 by root 2, right? So 1 by root 2 is where they intersect. And 1 by root 2 is approximately 0.7. So if I were to add 2 of them, I would get a point as 1.4 something, which happens to be exactly root 2, which is of course 2 into 1 by root 2. So I have this point over here. And now let us go to some point between these two. Well, at least for me, it looks like this part and this part exactly cancel each other out. So I'm guessing that there's a point where you have nothing in between. And when we go to this point, we have already sketched this. And let us graph between these 2 points. Due to symmetry, you can guess that this is going to be negative root 2. And then you can probably guess that there's going to be a point somewhere over here where the positive and the negative cancel out. So you have a point of 0 and back to this one. So if I were to make this infinitely continuous, I get something like this. And this is correct. This is the graph of sin x plus cos x. And let us graph it to be sure. Let's just disable all of the previous graphs and sin x plus cos x. And since we graphed it only from 0 to pi, let us stick to the same thing. Oh, we graphed it from till 0 to 2 pi. So this is the graph that we have obtained. And looking back, yep, this is exactly the same. But the thing is, if I were to graph another something different, like let's say square root 2 into sine x minus pi by 2. Okay, not minus, plus pi by 4. Well, you're like, why did you graph this completely random graph? Well, these 2 graphs happen to exactly superimpose. And you might wonder, how is it possible that 2 graphs are looking exactly the same? Well, there is a simple identity. I don't know if you remember or not, but I mean, more than an identity, this is algebraic manipulation that you should be familiar with. So let us take the sin x plus cos x and just multiply by root 2 and divide by root 2. And we'll take this division by root 2 inside the brackets. So what I have is something like sin x into 1 by root 2 plus cos x into 1 by root 2. And we can write this 1 by root 2 as cos 45, and this 1 by root 2 as sin 45. And like from that, we can basically use the trigonometric identity, which gives this as sine of x plus pi by 4. So that is how this is an alternate way of sketching the graph. But I want you to recollect from previous video that this looks extremely similar to shifting of origin. You might be wondering, how is this related? Well, let me show it to you. So basically what I've done is, I want to take this purple color graph and shift it a little bit behind so that it passes through this point negative pi by 4 comma 0. So if I had to do that, what I would basically do is, okay, let us name a point a comma b, and let a and b be such that a is equal to negative pi over 4 and b is equal to 0. So this is the point, and I want to take this purple color graph and take it and make it such that it passes through this. So what I'll do is, I'll replace y with y minus b and x with x minus a. And guess what? Since b is just 0, y minus b doesn't make any difference. So I can just get rid of it altogether. And sine x minus a is sine x minus pi by 4, which simplifies to x plus pi by 4. And guess what? Since we know that this purple graph is just, the green graph is just a scalar multiple of the purple graph, I can just modify this for some constant k and make it exactly superimpose. So this is another way of arriving at the same graph. You should have an understanding of both of these techniques, as they are both very important. And then you have your standard graphs. Since I've explained sine x and cos x, sine x in so much detail, I'll be rushing with cosine and secant, etc. And cosine x is basically sine x itself, but it is shifted to this point, which happens to be minus pi by 2. So if I had to shift it to minus pi by 2, what I would do is just subtract it by minus pi by 2. And voila, you get the same equation, same graph. And in fact, that is how you get the result cosine x is equal to cos x plus pi by 2. And this sums it up for cosine. And then you have your secant x. And when you're trying to analyze secant x, I highly recommend you to keep cosine x right below it. Because if you're able to graph cosine, then wherever cosine tends to 0, your secant tends to infinity. And whenever your cosine tends to negative 0, like from this side, your secant tends to negative infinity. And similarly, as your cosine tends to negative 0 again, like this, your secant x tends to negative infinity. And same thing, when it's positive 0, it's positive infinity, and when it's near 1 or negative 1, they coincide. And same logic with sine x and cosecant x. So when it's at 0, when it's positive 0, it's positive infinity. When it's 1, it's 1. And when it's positive 0, it's positive infinity. Negative 0, negative infinity. Negative 0, negative infinity. That's how I remember my graphs. And then you have your tan x and cot x. And these are pretty standard graphs. You can reason as to why the graphs look like what they are. And another interesting thing that I want to teach you guys is, how do you identify sine x? Okay, so first let me take up the drawing board. Sine x and y equals x. Well, these are pretty important things, and I'll explain why. So, okay, this was a pretty bad line. So, let us say I have let's say I have a circle. All right, I give one person, let's call this guy person 1, person 2, person 3. Drawing on the same Ferris wheel comparison, one person is given the task to compute the ratio of opposite and hypotenuse, and this is adjacent. One person is given the task to compute the ratio of opposite and hypotenuse, and I will basically give him that much money. And I give player 2, so this is opposite by hypotenuse, and I give the player 2 or person 2 the amount of money that is the ratio of opposite by adjacent. And I give player 3 or person 3 the amount of money. Wait, how did that happen? So the amount of money that the angle he makes with the positive x-axis or the ground. So this guy gets the angle, amount of money. So at any point, let's say at this point, how do you determine who the richest person is? Well, let's consider hypotenuse to be 1 in this example. So person 1 basically gets, and let us take theoretical numbers for this example. So let us say this is of height 0.7 meters, and the x coordinate of this is, let's say, 0.2. So person 1 basically gets the entirety of 0.7. So I have to pay him 0.7 rupees, let's say. And person 2, opposite by adjacent, which is 7 by 2. And 7 by 2, 0.7 by 0.2 is essentially 7 by 2. And this guy gets 3.5. And this angle will approximately be something like 1 point, let's say 4 or 1 point, okay, let's say 1.4 radians. So what we have is 3 different values. So if you had to arrange them in increasing order, you have 3.5 greater than 1.4 greater than 0.7. And this is basically your sine, and this is basically just your angle theta, and this is tan. And in order to verify this, let's just go Desmos and delete these. So from our previous conclusion, what we got is tan theta should be at the highest. Okay, let us start from lowest. Lowest was sine theta. So what I'm expecting theta to be is a straight line that is just greater than this all the time. And is my guessing correct? Yup, I'm absolutely correct. And similarly, tan theta should be greater than even this line. And yes, I happen to be correct again. So that you will be using this sort of this logic is actually very important in limits, where you have to know that sine theta is smaller than theta all the time, while tan theta is greater than theta all the time. Well, I think this sums up trigonometry, graphing at least. Actually, no, I can pull the video a little bit longer. I can teach you something that is also super important. In fact, my JEE Advanced asked questions on the very exact same topic, and that was the easiest +4 in my life. Let's discuss the effect of squaring sine graph. If you know what the effect on sine graph is, you'll automatically know what the effect is on cosine graph. So if sine is this, what's squaring? So if this is sine power 1, then sine power 2, since these are all fractions between 0 and 1, when you square a fraction, it's going to give you a smaller number. So these are all smaller numbers, but 1 square is just 1 again. And I'm going to get this, and I'm going to get something like this. Well, my graph sucks, but it should be connecting over here. So it kind of looks like as though here, and this is your sine square. It looks as though it became just a little bit sharper. But remember, sharp is not the right word to use, because if you technically zoom into it, at this point, it is technically still smooth. It's smooth everywhere. Sine square is also smooth everywhere, but you can say that it's narrower. Yep, that's the right word. It tends to be narrower. And if I increase the power, let's say sine power 4 or sine power 3. Oh, you guys kind of did not notice my mistake. Let me just show it to you. Well, control. Sine square is always going to be positive value. So it's going to be like this, but it's not going to become negative. So whatever graph I had previously is correct, but it's mirrored the opposite way. Since sine, when you square it, it automatically becomes positive. So this is how sine square would look like. And if I had to draw sine power 3, you would get the previous, like the initial graph that I did. Well, I'm really bad at graphing, but I hope you get the point. Just shift this over here. So yeah, as you increase the power, it gets narrower and narrower. But just remember, if it's even power, it's never going to be negative. So let's just use the example. I'll make this dotted lines. Okay, let's keep this solid. And sine x whole power n power to, let's say, 4. See, it becomes just a little bit narrower. 6 more narrower, 8 more narrower, 10 more narrower, and at 12 you get the previous graph. But just remember, it's always positive even at the other half. Even if your sine is negative, your sine square or sine power 4 will be positive. And let's try odd numbers. So it becomes sharper, but here even your negative values are included. So now you have sine power 5, sine power 7, sine power 9. So as you can see, it just becomes sharper and sharper. And now the real question that you have to understand is, the real question is, how is this useful? Well, in my JEE Advanced, there was a question, how many solutions from negative pi to plus pi does sine power 8 plus cos power 4 half. How many solutions from negative pi to plus pi? The genius that I am just took less than 20 seconds to graph it out real quick. So they asked minus pi by 2. This was included, by the way. Minus pi by 2 is included, and pi by 2 is also included. So if I were to graph this real quick, so I know my sine x is gonna look my sine power 8. I was superimposing my graphs. So my sine power 8 is gonna be very negligible in the beginning, and at pi by 2, I get a sharp, not a sharp, but you know the word, but I'll still use the word sharp, but just remember it's not correct. So I get this huge bump over here. And same thing, negative, negative, it's super small, and there's this bump. And cosine is the opposite. At 1, there's a huge bump, and it dies out really quick and remains obsolete. And same thing over here. So if I were to add these two values of the 2 points that I've drawn over here, like the value of this point and this point, so essentially by superimposing, I'm going to get an extremely similar graph that looks like I've just added the two graphs and drawn them together. And I've asked the solution of this is equal to 1. And I can just draw the straight line x is equal to 1. And guess what? I see one big solution over here, one big solution over here, one big solution over here. So the answer is 3. And this is very frequently asked. And knowing how to graph this makes sky and earth difference. So I hope you guys learned a bunch of new things in this video. And see you guys next video, I guess.